So what I have done here is that I have already shown you these tables. I have created 6 tables, and basically these tables are same. So customer CSV and customer Parquet are exactly same. The difference is that customer CSV points to a location in S3 with CSV files, and Parquet points to a location with Parquet files. Same is the case with order CSV and orders Parquet, seller CSV and sellers Parquet. And if you see the glue data catalog in 3IAM database, these are the tables that I have: customer CSV, customers Parquet. And if you look at the location, we have this folder 3IAM Athena dataset, performance optimization, customers underscore CSV, customers underscore Parquet, orders CSV, orders Parquet, sellers CSV, and sellers Parquet. And if I look at the folders, and this is the folder performance optimization, and look at the customer CSV, I have approximately 11 GB of file. Similarly, I have in Parquet also, I have too many objects actually. So these objects were created using glue. So the number of objects are very high, which is not a good practice, by the way. It will not provide substantial performance gain from CSV. But anyway, each Parquet file is of size only 32 MB, which is not good. So I should have optimized the glue job, or the Spark job rather. But anyway, so then we have orders.csv, and the size is 9.1 GB of the CSV file. And in orders.parquet, orders underscore parquet, I think again there are a lot of files, 145 objects, each of size 32 MB. Same is the case with sellers also. Now what am I going to do is that, so I'll run this query, and if you see I'm joining orders CSV table and customer CSV table. Let me execute this. All right, the execution is complete. Now if you see, this particular execution took 9 minutes and 49 seconds, and it scanned 20.5 GB of data. So a lot of data were scanned, even though I had selected only order ID, order date, customer name, email, and payment method. Only 5 columns were selected, and the data scanned was approximately 21 GB, and it took 9 minutes 50 seconds. Again, the execution time, or this particular time, was not for the data scan, because if you see the results, so the output contains 500 million rows, and it takes fair amount of time for these many rows to be written to the console. So most of the time was taken because of that to show the output in the Athena console. Now what will I do? I'll run the exact same query, but this time with the Parquet files, not the CSV file. And in case of Parquet, if you see, the data scanned was 4.73 GB, which is almost 1/4 of the data scan in CSV. But the execution time is 9.5 minutes, which is fine, as I said. So it is returning approximately 500 million rows. So the most of the time were taken to show the row in this particular Athena console. But again, what I'm trying to show you here is that data scanned is 4.73 GB as opposed to 21 GB. Now, if I execute this query with the limit clause, then the runtime would not be that high. Let us go ahead and do that. So in the Parquet file, I have put a limit of 1000, and if you see, the data scan is 4.62 GB, again similar to what we have seen previously, and the runtime is only 2.3 seconds. So it tells you that the 9 minutes was because to show the records here in the console. Let me execute the same query in CSV also. Okay, in CSV it scanned 17.15 GB, and it took 5.5 seconds to execute, almost twice as that of the Parquet file. And if I reduce it, let's say if I execute with 100 rows or limit 100, the data scan would be similar in both the cases. 4.66 GB and 2.366 is the execution time for Parquet, and for CSV it would be similar. The data scanned is 17.15 GB, and the execution time is 5.5 seconds. And if I look at the query stats here, the execution took 5 seconds for CSV, And for Parquet, the execution time was only 2 seconds. So for CSV, it was 5 seconds execution. In Parquet, it was 2 seconds. So you can imagine it is 2.5 times lesser. So that's where storage optimization plays a very important role in Athena performance tuning. Okay, so now we can look at the explain plan also. So if I click on this query, so click on explain, it would open in a new page or a new tab, and it shows the distributed plan and the logical plan. So if you see, the distributed plan has stage 1 and stage 2, and there are certain operators. So we have scan filter project, scan project, and then output. So here there are multiple operators: remote source, local exchange, remote source, inner join, output. So these are all logical plans, right? Because what is happening is we are looking at both distributed plan and logical plan. So each stage is executing these many stages or fragments. And if I look at the logical plan, so what is happening here? The first one is scan project. So what it is doing, it is basically scanning the table customers underscore Parquet, and project locality is local. After that, it is doing a remote exchange. It is doing a repartition, and the hash column is basically the customer ID, the hash value 6. So this is what is happening in the customers. And in orders Parquet, it is doing a scan filter project. It is doing a table scan, then it is doing a filter based on the customer ID, and then it is projecting only the columns that are needed. So it's not that it is projecting all the columns. So after that, it is doing a remote exchange for the orders table, and for the customers table, after doing the remote exchange, it is doing a local exchange after the remote exchange is done, meaning that the columns or rows were sent to different nodes from one node to another node, and there it is sending the value to the other stages, and then it is doing an inner join of these two tables, and finally the output. So now these are the stages that you can see, right? And in the distributed plan, actually the stage 1 is scan filter project of the orders table, and stage 2 is scan project of the customers table. And in stage 0, everything is happening. So if you see here, we have remote source, local, then local exchange, then again remote source, inner join, output. So these are the fragments that are getting executed in stage 0. This is how we can look at the explain output. Not only that, we can actually type explain here and maybe mention type logical, and then execute this, and it will give us the query output plan. It can be a little difficult to understand, so that's why it is better to look at the explain plan pictorially, which you can get using this explain button. Okay, now one of the most important things, Athena pricing, and I'm considering the region to be North Virginia. The first thing is Athena SQL, which essentially is Trino. Now here we do not have to pay anything for the cluster. So the pricing is based on the amount of data that we scan, and we have to pay $5 per terabyte of data scanned. Now let's say if you are joining 3 tables, each of size, let's say 10 GB, then if it's a cross join or Cartesian product, we might be scanning 1 terabyte of data, meaning that as it is a Cartesian product, and we have 3 tables of size 10 GB each, so 10 into 10 into 10 is equal to 1000 GB, approximately 1 terabyte. So the cost would be based on that data, right? So for all the data that Athena SQL is scanning, the cost would be, or the pricing would be based on that. When you execute queries in Athena, we see this data scanned, which actually gets increased. So here it is showing only 6.74 GB. So the pricing is based on this, how much data has been scanned. And this is for Athena SQL. But if you are using provision capacity, using capacity reservation that I have shown you in WLM, so we create a work group, then we make capacity reservation, and then we associate the work group with the capacity reservation. And then whatever query we run, those queries in that particular work group will use the DPUs that we provision. The pricing is basically for one DPU. One DPU, each DPU would cost 30 cents per hour. And if you are provisioning, let's say, 60 DPUs, it will be $1.8 per hour, because 60 into 0.3. Then we have Apache Spark also, and in Apache Spark also we have to provision DPU, and the cost is little higher, wherein we'll have to pay 35 cents per DPU per hour. Of course, let's take an example. So let's say we have two statements. One is we have approximately 2 terabyte of data being archived from Redshift to S3 every month, and it is kept in S3 for 6 months and then expired. This is an archival process from Redshift to S3, which is the best practice, right? So we have to make sure that we archive from Redshift. And what happens, we run only 5 ad hoc queries every week, which reads approximately 8 terabytes of data because of complex joins. So what would be the pricing? And then let's say we have dedicated compute capacity, which is needed for batch queries, and we have provisioned 50 DPUs, and 40 to 45 DPUs are used weekly for 1 to 2 queries that run for 8 hours, because we want to give dedicated compute resource. So what would be the pricing of this? So I have taken example for Athena SQL and provision capacity. I'm not showing you the example with Apache Spark. Let's try to decode these statements or find out the price. So here it says that we have approximately 2 terabyte of data being archived from Redshift to S3 every month. So let's say this is how the storage is, and it is expired every 6 months. Now this is from the beginning, right? So let's say the project has started. Let's say from next month onwards, the archiving would happen. So in the first month, from Redshift, we'll archive 2 terabytes of data. On the second month also, we'll archive 2 terabytes of data, but S3 would contain 4 terabytes. 2 terabytes from month 1 and additional 2 terabytes for month 2. For month 3, again, same story. So we'll have 6 terabytes stored in S3. For the 4th month, it is 8 terabytes. 5th month, 10 terabytes. And 6th month, 12 terabytes. But the requirement is as such that the records are also, or the files are also kept in S3 only for 6 months, and then it is expired or moved to some other storage like Glacier or Glacier Archive or something like that. That means month 7 onwards, what would happen is 2 terabytes would be added for month 7 and 2 terabytes would be removed from month 1. So it is nullifying, and we'll have only 12 terabytes of data stored in S3, and the story would continue thereafter. So always we'll have 12 terabytes of data, and the pricing should be as such. The pricing should not be on month 1 to 5. It should be from month 6 onwards, because the month 1 to 5 would be the initial pricing and will be there only for 5 months. And for the remaining time, for as long as the project is running, we'll have 12 terabytes of data in S3. So this is the amount of data that will be stored in S3. Then what about the data scanned? It says that 8 terabytes of data would be scanned by 5 ad hoc queries every week. Again, it does not say whether it is on 2 terabytes or after 6 months. So what I'll do is that I will assume that the 8 terabyte data scanning is on actually the 2 terabytes of data. So this is the worst case scenario, and of course while doing the pricing, we'll have to make this assumption that this 8 terabyte of data scan is out of the 2 terabytes that we are storing, and 8 terabyte is for 1 week. So for the entire month it will be 32 terabytes. So for month 1 it will be 32, then 64, 96, 128, 160, 192, then it will continue to be 192. Why? Because month 6 onwards it will always be 12 terabytes of data that will be stored on S3. So now how the pricing would be? For First month it will be $160, second month 320, then 480, then 640, because it is $5 per terabyte of data scan. For fifth month it is $800. For sixth month it will be $960, and it will be $960 going forward, because the data scanned is not getting changed. Of course, this is idealistic scenario. We can expect sometimes more data scanned, sometimes less data scanned, etc. But this is how the pricing would look like. So in our case, the cost of Athena would be $960. Along with that, we'll have to pay the cost of S3 also, because we are storing 12 terabytes of data in S3. So that price will not fall under Athena anyway. So this pricing is for the first problem statement. Let's talk about the next problem statement, wherein we need dedicated capacity for batch queries, and 50 DPUs have been provisioned. And 45 DPUs are used weekly for 1 to 2 queries that runs for 8 hours. Now here, there's no change irrespective of month 1 or month 6 or month 7 or month 8. Because it's a batch query and we have provisioned 40 DPUs, we'll not have to pay on the data scanned anymore. We'll have to pay on the amount of DPUs that are getting used, or data processing units that are getting used. And what it says that it uses anywhere from 40 to 45 DPUs by 2 queries, which run for 8 hours in a week. So if it is 8 hours per week, it will be 32 hours per month. And I'm considering 45 DPUs, not 40 DPUs. So how the cost calculation would be? So we have 160 DPUs used monthly, because for 1 week it is 45 DPU. So for 4 weeks it will be 160 DPUs. Actually I have considered 40 DPUs, not 45. Anyway, that's fine. So if it is 45, then it will be 45 into 4, because if 1 week it uses 45 DPUs, then in 4 weeks it will be 180 DPUs. Anyway, so I've considered 40. So the cost calculation would be 160 DPUs for the entire month, and a single DPU costs 30 cents per hour. So 160 DPUs would cost 160 into 30 cents, or $0.3 per hour. This is for 1 hour, and we have a total monthly hour of 32. So I'll have to multiply by 32. So this is how the cost would be, and it comes out to be $1,536. Right, so 160 DPUs and into 0.3 would give us per hour cost, and into 32 would give us monthly cost, because in the entire month we are going to use only 32 hours of DPUs. So the cost would be similar, the calculation would be similar for all the months, and the cost would also be similar for all the months. So this is how the pricing of Athena is, and if we use Spark, instead of 0.3 it would be 0.35 depending on the number of DPUs. So let's say Spark uses 50 DPUs, then it will be 200 DPUs used monthly, and if it is 8 hours per week, then 32 hours monthly, so it will be 200 into 0.35 into 32. That's how the cost would be if you use Apache Spark on Athena. So that's about pricing, and let's summarize section 2 and section 3. We have seen workload management, and we do workload management in Athena using something called workgroups, wherein we mention the amount of data scanned, and we can also get provision capacity using DPUs, or data processing unit. One DPU is 4 vCPU and 16 GB of RAM. Then when you talk about performance optimization, the most important performance optimization is the storage level optimization, because what happens is that as the data is not stored in the nodes physically, it is always stored on S3. The local exchange and remote exchange cannot be controlled. So the storage level optimization is the most important in Athena. So we should store in columnar format, and also we should compress the data always. Then I have also shown you explain plan, the various explain operators, and how you can look at the explain plan in console and using command line. Then at a very high level, I talked about Athena with Spark. Then I concluded with pricing example. So that's all in section 2 and 3, and in fact that's all in Athena. And before closing the section, I wanted to show you the various use cases or architectural diagrams where Athena can be used.